so second lecture this morning is the first lecture in the series on contact quality, not contact quality.
Well, thanks. So I'd like to thank the organizers very much for the invitation to give this mini course, and to all of you for having the fortitude to stick through all of the mini courses. Although I guess we'll see again on Friday. Okay, so I'm going to be talking about a theory, a non-invariant really called not-contact homology. It's an entire package that's associated to knots in free manifolds and also to various other objects that are related. And I'll try to first give a bit of an overview, and then we'll maybe that'll culminate in a brief outline of what we're going to do, and then we'll get into the rest of today. We'll be talking about HUN-REN contact homology. So if you know about HUN-REN contact homology and augmentations already, you can take the day off. There are lecture notes. I made this announcement before this. They're also on the website, and if you look through them, they're in fairly incomplete form, so I apologize for that. But I think it is better than that. Okay, so and this is partly based on some joint papers with a number of authors, all of whom have TBS. So there they are. Okay, so here's a quick overview. So the goal of this project is to somehow, well, this is the goal of a lot of people, and this is only going to be some small part of that, but to study these smooth topology of manifolds, smooth manifolds, or on submanifolds via symplectic topology of the HUN-REN. So this is something that Tobias mentioned briefly in his talk yesterday, and let me just tell you how the general setup goes. I think a lot of you know this already. So if you have some sort of, what is it need to be image? If you have some smooth manifolds, and so then you can look at this potential manifold. And this is naturally symplectic manifolds. I think you all know this. But just to remind you, the symplectic form is maybe minus b of the Liouville form, which in coordinates is PEQ, and you can describe it in more invariant ways as well. Okay, so that's a nice symplectic structure on the cotangent bundle. And if you further assume that the manifold is Riemannian, although it turns out that it's independent of the metric, then you can restrict to, you can just take the sphere bundle of this. So this is the bundle of length 1 covectors in the cotangent bundle, and this is naturally a contact manifold. And the contact one form on here, which somehow in my mind is always an alpha. So the contact one form is just the Liouville one form restricted to the cosphere level. Okay. Great. And so the question is, this is really just restating. So somehow the question is, how much does the symplectic or contact topology of these two things remember about the smooth topology of the underlying method? So symplectic contact topology T star n, cosphere bundle S T star n, remember about the topology, smooth topology. And what I hope to convince you in this lecture series is, at least in some circumstance, the answer is quite a bit. So just to talk about some results that I will really not be talking about at all, let me give some sort of prototypical results in this line. So here's a theorem that I'm purposely going to leave vague. So this says that you can associate various Floer homologies to the cotangent level. So maybe some sort of Hamiltonian version of Floer homology T star M, and this is supposed to be, so any of the experts in the audience should just keep your mouth shut at this point, because this is going to be very big. This is supposed to be somehow a singular homology or homology of the loop space, free loop space. This theorem can be interpreted in a number of ways. I'll just put up some of the people who have proven results along these lines. There are others. And there's also sort of related work by Tiliadov and Malchev, but using contact homology of the cosphere bundle and relating it to string topology on the manifold. So related work. Okay, but again, at this level of vagueness, what you should take out of this is just that there's some symplectic invariant of the cotangent bundle of manifold that remembers quite a bit about at least the homotopy type of the manifolds, sort of something along those lines. And let's see. There's also a great result from us that I will also not state precisely, but essentially says that you can distinguish various exotic structures, maybe some exotic structures in spheres, using the symplectomorphism type. So I think Tobias also alluded to this yesterday as well. So there's all sorts of nice things that you can get out of this. I'm not going to talk about any of these. So what I'm going to talk about is a relative version of this. So instead of studying the smooth topology of manifolds, what we're going to do is we're going to study the topology of submanifolds inside of your smooth manifolds, or what it'll end up reducing down to is essentially we're going to be studying some sort of knot theory using these sorts of ideas. Okay, so right. So the relative version goes as follows. So you have, I think probably most of you know this already as well, but anyway. So suppose that you have a submanifold. So there's no symplectic stuff going on yet. It's just an embedded submanifold inside of M. And you can think of this as a knot sitting inside of a free manifold, say. It turns out it doesn't even need to be embedded, so it could be immersed with, I think you need transverse self-intersections. Okay, so from this then you can get a submanifold inside the cotangent bundle, which I will write in relation to, okay. Right, and this is the conormal okay. And everybody knows what the normal level is, so this is just the dual concept, and in fact this one's a little bit more natural in some sense because you don't have to choose a metric on your manifold. So this is just the set of points in the cotangent level, say QP, such that Q is in K, and P, so P is a covector at the point Q, and it's supposed to annihilate all tangent vectors to Q, to K x Q. So total would be T Q K. Okay. Let's see. Okay, so let's draw some sort of rudimentary diagram of this. So here's M. Here's the cotangent bundle to M. I'm actually going to, somehow I have trouble drawing infinite things, so I'll just write that this is the disk cotangent bundle of M. And here's, let's see. So from sitting in the audience for a while, I learned that colors are completely not visible. Is that correct? They're indistinguishable from white. That's okay. I'm going to use them anyway. Okay. Okay, so that's K sitting inside of M, and then lying over it somehow is this LK. Okay. Great. And you can furthermore intersect with the, so if you want to deal with compact things in this context, then you can instead look at the sphere bundle. So then you can also define lambda k. So this is just LK intersecting with the sphere bundle. And this, of course, is inside the S. So lambda k is really just easy that. Okay. And this is the unit normal. Okay. And then it's a standard fact. It's actually one of the exercises. I think it's exercise 3. So all of the exercises are in the back of the handout, so you don't have to write this down. So the exercise is that LK is the Lagrangian, and lambda k is the Lagrangian. And this word has come up a bunch, but let me just remind you in case it's not familiar. This just means everywhere tangent to the contact hyperplane. So that's not quite it, and also of the correct dimension. Correct dimension. So that just means it's the maximal possible dimension, so that this condition holds. And in this case, it means if n is n-dimensional, then this thing right here is 2n minus 1 dimensional, and this is n minus 1 dimensional. So, the point is that this allows you to take something that was just sort of sitting in the smooth category, so you have a submanifold sitting inside of M, and allows you to sort of drag it into symplectic or convex topology by using this conormal construction. Okay, so for me, so this Lagrangian, I guess, will pop up again later on at some point, but the key thing is going to be this Legendrian submanifold inside of Victor's curve. And the point is that if k changes by smooth isotopy, then lambda k changes by Legendrian isotopy. So that means just an isotopy through Legendrian submanifolds. And so at this point we know quite a bit about Legendrian submanifolds up to Legendrian isotopy. So it's sort of reasonable to pose the question, so what does the... I keep writing out questions. These are actually all basically refinements of, so each question is a refinement of the previous question. So the question is, what does the HUN-REN type K remember that? There's the button type. So this is a nice, fairly general question. I'm now going to start specializing. So the first thing to do is to restrict to M to Rn. N is going to be 3 in a second. And the exercise, so there's a standard exercise that says that, in this case, so S2 star Rn, with the context structure that I described, it's now gone, but what I described before, this is actually adaptomorphic to the one-jet space of Sn minus 1. So what's the one-jet space? And this is something really most of you know, so I'll just say it briefly. So the one-jet space of the manifold is 2 star M cross R. And this is naturally a contact manifold, so contact form. So this is going to be dz minus lambda canonical on T star M. Sorry, small. So here z is the coordinate on the r direction, and so this is, if you like, for instance, if n is equal to the real line, then this is the usual contact form dz minus y dx. And generally you can do this, so there's some sort of natural contact structure on the one-jet space of the manifolds. And it's an exercise that these two things are the same, so they're obviously diffeomorphic. Checking it, so they're contactomorphic, and in fact, there's a contactomorphism, there's a diffeomorphism that sends the contact form on one of them to the contact form on the other one. Not just the contact structures. So that's one of the exercises. Okay, so this seems like an irrelevant comment right now, but it'll come up again because some of the invariants that we want to use are defined on one-jet spaces, so it's actually important that the contact manifold we're starting out with is a one-jet space. Okay, so let's further restrict to terms of 3, and K is a knot. And I should say, everything I'm going to say works perfectly well for links. For purposes of exposition, I'm going to restrict to the case of knots, but maybe once in a while I'll say what happens for links. Okay. So then, in this case, then the contact manifold, which is the Kurzgesagt bundle of R3, so this is the same thing as the one-jet space of S2. And what about this lambda k? So lambda k, so this sits inside of the one-jet space of S2, which topologically is S2 plus R3. And lambda k is going to be diffeomorphic to, well, it's just a surface, and then the surface is just the two force. And the way that you can think about this is just think of this as, the definition is still there. So it's supposed to be the unit conormal, right? So if it were the unit normal bundle instead of conormal bundle, then you can think of it as the boundary of a particular derivative of knot. So that is actually sort of how I think of it. So think of this as the boundary of a tubular derivative. So here's K and here's lambda K. Okay, so the boundary particular neighborhood of a knot, of course, topologically, it's just T2. That's the first part where, I guess, where like, it becomes a little bit more complicated. There it's a union of, disjoint union of two drawing. So it turns out that if you let your knot vary, so you look at what you get out of different knots, so they'll all give you two tori, and topologically these are actually all the same thing inside of this five-dimensional space. So for different k, all of these lambda k are smoothly isotopic. Smoothly isotopic. So that's an easy exercise, which is also some of the exercises. But not necessarily Legendre isotopic. So if you require the isotopy to remain as an isotopy of Legendre submanifold, and in fact, a lot of these lambda k's will turn out to be different things. So let's get let me rephrase this question here. So here's a concrete question. Okay. So the question is, if you have two knots and their unit conormals are Legendre isotopic, are K1 and K2 necessarily the same knot? So the answer to this in general is unknown at this point, which leads to the optimistic possibility that the answer might be yes. And that's not this going from a knot to its unit conormal might actually remember everything about the underlying knot type. So in other words, I don't actually know of two knots where that are distinct, but their conormal modes are actually Legendre isotopic. So here's a partial answer. The partial answer is yes, if one of them is the knot. So the lambda corresponding to the unknot is different from lambda corresponding to every other knot. And we'll see this at some point during the course. Okay, so now has come the time when I can give you an outline of what we're going to do in the course. And maybe I'll write this as some sort of set of boxes or flip chart or something. So on this side we're going to have smooth topology. On the other side we'll have some project. So you start off with a knot K. And then through this construction, which I call the conormal construction, so you get from here to, oh, by the way, this is all, everything that I've said so far, this is all pretty old stuff. Been floating around for a long time. So you end up with a Legendre 2 torus. Okay, so this is sort of drag things into some collective world. And I mentioned that there are lots of things I know about Legendre isotopy types of things now. And in particular, there's a very strong invariant that is called Legendre convex homology. That is way too long, so I'll probably abbreviate it as LCH. And this is an invariant of certain Legendre submanifolds of things, as we'll discuss in a second. And out of this, you end up with some graded homology theory, which I'll write as this, HC star of K. I know there's some dispute about what order to write the letters in. Homology content star of K. So this will It's called non-contact homology. So I have this on the symplectic side, but really, well, I guess there's no symplectic side. Okay, so that gives you some sort of knot invariant. And this is something that you can actually describe combinatorially. So that's one of the nice features of this subject is that to go from here to there, it requires some sort of counter-homomorphic disks, as we'll discuss. But once you can actually do the counter-homomorphic disks once and for all, and there's some combinatorial way to get this done, which we'll talk about during the mini course. And so then you can drag this sort of back over here. There's a topological interpretation for this invariance. Involving what's called the chord algebra. And there's also, in addition to that, there's some sort of somewhat relatively painlessly, I got stuck in the middle of that sentence. There's some way to get a polynomial out of this, which is a three-variable polynomial, and it's what we'll call the augmentation polynomial. Oops. So that's going to be a three-variable non-invariant. I won't write it down because we'll talk about this at length at some point. And then what? So if you stay over on the symplectic side, there's also some way to get applications of this invariance to contact geometry. So one of them is through what's called transverse homology. And what this is some sort of additional structure on this invariant if K is not just any knot, but it's actually a transverse knot, so it's not transverse to a contact structure. Invariant of transverse knots. And it's actually a pretty good one in some sense. And back on this side, there's some recent developments that there seems to be some link between the augmentation polynomial and this other stuff with the conflict polynomial. And maybe one other density homology. I should put question marks on these, depending on how much I actually did go through. So there's something that it appears that you can get from this sort of stuff here, this three-variable polynomial, to things like the conflict polynomial, or at least part of it. And these other things, and we'll discuss this some point in the mini course. Okay, so
what if K is Legendre?
So if K is Legendre, it appears that you get some additional structure on here. I don't actually know what it is. So we can write it down explicitly for transverse knots, and there we'll see that it's sort of a natural thing to consider. For Legendre knots, it seems like you should be able to do something similar, but we don't actually know what it is or whether it's good for anything, unfortunately. Okay, so this flowchart here, this is the, you can tell this is the outline for the lectures. So, lecture 1, Legendre contact homology. Lecture 2, contact homology. Lecture 3, the chord algebra and the augmentation polynomial. Lecture 4, transverse homology. And lecture 5 is this new stuff, which brings in some string theory, some work with synthesis, and this is going to be given by Tobias, who is kindly relieving me of many course duties for the very last lecture. Okay. Sound good? So now we can start it. So I have another hour. Well, I have serious doubts that I'm going to actually be able to stick to the schedule, so there's probably things are going to slosh over into future lectures, and hopefully I'll be able to finish off my part of the mini course before lecture 5. It'll be done one way or the other. so are there any questions? So what I'm going to spend the rest of today talking about is legendary contact homology. I think a lot of you know about this already. It's maybe not quite as well known as just regular contact homology or say embedded contact homology. So I'll give you at least the setup, and so at least you can see how it's supposed to be set up. But then what's going to happen is that starting next time, I'm going to ignore sort of all symplectic geometry and it will become combinatorics or algebra or something. So here's the setup. So the setup is that we start with a contact manifold B, and in fact, I'm right away just going to assume that it's one jet space of some manifold. It's not fact. So that this is going to be my contact manifold. You can do this possibly in other cases, but I don't want to think about them. And lambda sitting inside of B is going to be a Legendrian submanifold. Okay, so if you have such a thing, then you can take the symplectization, which is just you cross B with R. Symplectization. So maybe, I don't remember if this has been used yet. So let's say, how do you get a symplectic structure on this? Well, you can just write omega is B of B of C alpha, where alpha is the contact form on B. So this relies on the contact form on B, which is a gate to know. Okay, so this gives us a symplectic structure on R cross B. And then you can also then cross the Legendrian with R, and this is now a Lagrangian submanifold sitting inside of R cross B. And so again, another definition that I think everybody knows. So a rate chord lambda. So well, you certainly all know about rate orbits. So this is just the relative version of that. So it's an integral curve. So the rate vector field R alpha. With endpoints. And I should specify, in this particular case, where V is the one jet space of M, so V is the one jet space of M, which is 2 star M plus R, and this R has a Z coordinate on it. So the rate vector field corresponds to the usual one form that I already had before. This is just V by dZ. And for those of you who are interested in technical things, so this is sort of nice. One reason that we restrict to this particular case is because in this case, then there are tiny closed rate orbits. Whereas this, that's okay, this is non-compact. So that'll just make the setup of Legendrian contact homology a little bit easier. So, Legendrian contact homology is the homology of a differential gradient algebra. Which I write as script A D associated to lambda. And this is, I guess, originally this is work of so what I'm going to do is I'm going to describe this differential gradient algebra to you, and also because I don't want to follow, I'm going to And to define this, I'm going to make some simplifying assumptions, and one of them is that lambda has finitely many breakpoints. And the breakpoints, if it has finitely many of them, then we might as well label them. Let's say it has n of them, I'm going to label them just formally as A1 through AN. And I'm also going to assume that there are generic intersections. And I'll just put generic in parentheses and let you interpret that how you will. Okay. So the other thing I want to assume is that, so this is not necessarily that it'll make the description easier, and it's all that we actually need for non-practical technology. This is going to be assuming that as trigger a Maslov class, which just means that the Maslov index of any closed loop in lambda is 0. Okay, that part may be controversial. Like I said, you can do this when lambda doesn't have to be a Maslov class, but it involves more notation and to keep things simple. Okay, so what I'm going to try to do for you now is to define this differential-graded algebra. And the differential-graded algebra has 3 parts. So the algebra, the grading, and the differential. And let's say I'll tell you about 2 of these 3. How's that? Okay, so well, I can tell you about them. Okay, so here's the algebra. So I'm going to write down a series of unhappy, well, it's okay. I like the group that no, 3 non-commutative unital algebra over. So there's going to be coefficient rate R, and this is going to be the group ring of H2 of D lambda. So this is relative H2 of the contact manifold, rel the HUN-REN submanifold. Generated by wave force. Okay, so I'm going to abbreviate this by A is R-A-1-N. And this is not a vector space. What this is actually, another way to say this is the tensor algebra over R that's generated by A1 through AN. So think about the polynomial algebra generated by these things. But now, don't allow the AIs and the AGs to compute with each other. Okay, so generators over as an OR module. Generators look like AJ1 through AJK. So it's some product of the A's, and here again the order matters. So this is not a commutative thing. Indices can be repeated, that's no problem. Not only can they be repeated, there could be none of them. So you could have nothing here, and what's nothing here? So the empty word, so this is the word here. So the empty word we write as just 1, and this is inside of, it's just the usual element 1 inside of R. Okay, so this looks sort of, for those of you who are used to other homology theories, some of them look a lot simpler on this level. Somehow you have a lot of stuff here, right? So first of all, this is pretty big. And secondly, it's not finitely generated as an OR module. And thirdly, there's a multiplication operation on there, right? So you can multiply words by just concatenation. So those are all sort of possibly unusual things depending on your background, but just bear with me, this will be okay. Okay, I should say something about the grading probably. So actually, the key thing that I'm going to say about the grading is that so there's going to be a gradient on these things, and anything that's in the coefficient ring is going to have gradient 0. The AIs are graded by gradients to do this with it. More chocolate from the noise. Are graded by these indices. I don't really want to talk about this, so I'll just leave that as a black box. And that's enough to grade the whole thing. So if you have a gradient on each of these things, then you just extend the gradient to the entire algebra. So the gradient of a product is the sum of the gradient. It's a x, y. Its gradient is x plus y. It's like what you would do with a polynomial gradient. Okay, so far so good. The last and most important piece, and the one that requires a little bit of time to say something about, is the differential. So what I'm going to do is I'm going to define the differential of each of these grid chords AI, and then extend to a differential on the entire thing by two things. So one of them is the differential of any thing in the coefficient ring is 0, and the other thing is the signed Leibniz rule. So d of xy, so d of xy plus those times the, sorry, gradient of x times d. Right? So what I have to do is just tell you what the differential is on the AIs. Okay. So, in order to define the differential on the AIs, I have to somehow inexorably talk about homomorphic disks. And so, suppose that you have an AI and some number of elements, I guess it's here, and some collection of grid chords AJ1 through AJK. These don't necessarily have to be distinct. They're just things. And how many of these are there? There's at least the AI, and then there's these AJ1 through AJK, but K could be 0, so there might just be none of those. So the first thing we're going to do is we're going to define a moduli space AI semicolon AJ1 through AJK. And this is going to be a moduli space of J homomorphic disks. So what is J? So J is going to be some sort of compatible, almost complex structure on this conservation. So I think, by the way, that this part of the definition, probably a lot of you have seen, or at least I've seen in the closed case when you don't have HUN-REN. So I'm going to go through this pretty quickly, I think. Also because I don't actually want to say much about it. So this is going to be an almost complex structure compatible with the conic structure in conic form on B. So if you want to be precise, this says that J of related T is the rate direction, and J maps the convex hyperplanes to itself. Again, not going to get into details. And it needs to be translation line invariant. So if you have such a thing, then I just want to note one thing. So then note that R cross AI is a J homomorphic strip. draw this is, so this is the R direction. Here's the lambda. So this whole thing is R cross lambda. And here's AI. And then you just take the cylinder over AI, this thing here. This is a J holomorphic strip just because of this condition here. So again, d by dt is the R direction. And yeah, so this follows from the fact that AI is a rate chord. Okay, so I think now we can start to define moduli space. So this is going to be the space of J holomorphic maps, which I'll write as delta. And this is going to go from, I'll draw a picture in a second. Let me write it down first. Okay, so what is this thing right here? This is a disk. So here's the D2, and here there are going to be a number of punctures in the boundary. D1 minus 3 pk minus. And you'll notice that I've drawn them in order around the circle. So as you go around the circle counterclockwise, you're supposed to reach them in order. And this is going to be mapping into, so let's see if I can draw this out. This is R cross D. This here is R cross lambda. And what I want is I want this holomorphic map into there to look like, well, at either end, the positive or the negative infinity end, it's going to look like one of these holomorphic strips. And initially it's going to do whatever it wants to do. So let's see if I can go else. I can't go on with you. Okay, so this part up here, this is going to be going to be AI. And these bits down at the bottom are going to be, sorry, the screen down here, going to be AJ1 through AJK. So this is going to map into something that looks like this. So does that diagram make sense? So what's happening is this puncture right here is getting mapped to sort of up at infinity to AI. And then these punctures down here are getting mapped down at minus infinity to AJ1 through AJK. And where does the Legendre come in? Well, the boundary of this holomorphic disk is supposed to lie on this Lagrangian cylinder. So those pieces right there are all lying on R cross lambda. Okay. So that was a picture I know let me at least try to indicate what the important thing is here. So this is supposed to be, I guess the one thing that I didn't write down, but I sort of drew, is that this is supposed to be asymptotic to the A's, the relevant rate chord is at plus or minus infinity. So this is, asymptotic to AI at plus infinity near P plus, and AJL minus infinity near B minus JBL minus. Okay. Okay, so this is something. So acts on this moduli space by translation. So this is because of the translation invariance of the almost complex structure. So if you have such a holomorphic disk, you can sort of push it up or down, and it will remain holomorphic. And now, finally, I think I can define the differential. So remember, I was supposed to define the differential of AI. So there. So this is going to be the sum over all moduli spaces. So if you multiply the R action, the dimension is supposed to be 0. So these are sort of rigid up to translation or transition. And then for each moduli space, what you do is you take. So if this is dimension 0, then it consists of a bunch of points. Each point I'm just going to label as a disk delta. So if you have a disk delta inside of M mod R, so there's going to be some sign associated to delta, which I'm not going to talk about, but involves, so to choose signs, you have to choose some sort of covariant orientations on moduli spaces. I want to talk about times. So I'll write it as e to the class of delta. So let me finish writing this down, and then I'll explain. And also not space. This keeps going down here. AJ1. Okay, that's the end of the definition. So let me say what this is the class of delta sitting inside of H2 of the. So I guess delta actually maps into R cross V, but you just project out the R direction, and what you end up with is you end up with a surface, right, and it has boundary on lambda. So this gives you an element in this relative homology H2 of V comma lambda. The one thing I'm going to highlight over is it's not quite a surface with, well, I mean, there's some issue with the ray cores, right? So if you actually want to get a class in here, you have to close up the ray cores. You have to sort of glue in some little auxiliary surfaces so that you actually get something that is closed in a sense. But I'm going to ignore that. And so this e to the whatever, that's just our notational trick for saying that you think of this as H2 as a multiplicative group instead of a negative group. So that's the definition of the differential. Right? So I told you I was going to define DAI, and that's what it is. I'll just note a couple of things. So one of them is that you can sort of start seeing why you need this entire algebra. So the point is that in the differential you end up with things that look like words in the AJs. So that's sort of naturally an element in your algebra. By the way, this word could be empty, in which case that's just the generator 1 inside of the coefficient ring. And that's it. So there's a theorem. So this is sort of talked about by Ashby and Hofer, but actually proven in this particular case. The assumption, so what I'm going to tell you is actually the Eichel-Sullivan result. So here, just remind me that V is J1, and everything is, let's assume that everything is suitably generic. So a few things. So one of them is D decreases degree by 1. Right, so this is a differential gradient algebra, and I didn't really tell you much about the grading, but the differential is supposed to decrease degree by 1. The second thing is that D squared is 0. And the third thing is that since D squared is 0, you can take its homology. And I'll write this as HC star of B lambda. So this is the Legendre contact topology. There's going to be variance lambda up to Legendre S copy. And actually also up to choices made along the way. So for instance, it turns out not to depend on the precise contact form that you've chosen, only on the contact structure. And this invariance is what we call the Legendre contact topology. Right. So maybe I have a couple minutes left. Let me not say anything about the proof. If you want to know about the proof, I'm happy to talk about it, but maybe another time, or after the talk. Let me just make a couple of remarks. And then we'll call it quits. So one remark is that note that the order of the AJLs matters in the potential of that. Or meaning we actually keep track of the order. So the point is that you can keep track of the order because these punctures on the boundary are carried in some order, so you might as well keep track of that order. So this is unlike the closed case. So the closed case, what do I mean by that? I mean, if you just talk about regular contact homology, then in that case, what you're looking at is you're looking at maps from a concentric sphere into the symplectization of some contact manifolds, and there the punctures are getting sent to ring orbits at plus or minus infinity, but there's no sense in which these punctures are actually ordered in any way. So that's sort of one key difference between the Legendre case, this relative case, and the closed case, is that you're sort of naturally led to consider this tensor algebra instead of just taking some polynomial ring generated by derivative course. Remark 1.5, which I won't write up, is that if your ambient contact manifold actually has closed ring orbits, you can probably do something similar to this, but what you're going to end up with is some more complicated object, which is going to be a module over the closed contact homology of the ambient manifold, or something like that. It's a little bit complicated to write down, so I won't do it. But nicely, in our case, there are no closed ring orbits, so we don't have to worry about that. The other thing is that there's some sort of notational issue. So there's this Legendre contact homology, which is the homology of this differentiated algebra. In some sense, the basic object that's invariant is not the homology, but the differentiated algebra itself. So there's some notion of equivalence on these differentiated algebras that's due to Chekhanov. So there exists a notion of equivalence for these differentiated algebras. And it's called stable team isomorphism. And since I've probably not left myself enough time to talk about this, I will refer you to the notes. And then the result is actually that the DGA associated to Legendre is invariant under this notion, under which this DGA is a Legendre invariant. And I had something to say about this. And so there's an exercise. So this notion, I really don't like this name, but anyway, it's just stable tame isomorphism implies quasi-isomorphism. In other words, if you have two DGAs that are stable tame isomorphic under this notion that I haven't told you, Chekhanov didn't me say this entire thing. Let me parse this. There exists a notion of equivalence for these DGAs called stable-state isomorphism, and under which this thing is a Legendre invariant. And he showed it for Legendre amounts of R3, but Echelman and Sullivan showed it for this case that I've described here. So anyway, the exercise is that this notion of equivalence actually implies quasi-isomorphism. So in other words, if two DGAs are equivalent in this way, then their homologies are actually isomorphic. So that implies 3 here. So the fact that the DGA is invariant under stable team isomorphism says that its homology is invariant. Period. So I think a lot of time. So next time I'll start with what I thought I would finish with today, which is defining computations for DGAs, and then we'll actually start with the combinatorial definition for not-contact homology. Thanks.
Are there any questions?
Yes.
When you say that the homologies are variant under a choice of contact form, you mean within the class of contact forms that have no closed orbits?
That's probably the easiest thing is within the choice of contact.
So what is what's true?
That's what they do, that's right. So I guess okay, so somehow I've already restricted this case where there's a particular contact form, and so I never think about this, but that's right. So you have to restrict yourself to things where there have to be those variables. Yes.
How restricted is the assumption that you have to put up with or the Legendre into the finite stage?
Sorry, what's the?
So you put some restriction like you have to have finitely many grade chords
Right.
on the Legendre. How restricted is that?
So the question is, how restrictive is the assumption that you need finitely many grade chords? And I think there's a more spots way of doing it. Well, I know Friedrich did the more spots contact homology, but for the closed case, I think maybe this also exists for the Legendre case, right? Very good. Yeah, so you can do this if there are infinitely many, but it's in that case it's sort of more natural to try to use some sort of more spot setting and work from there. Sorry, there's also the case where there are infinitely many grade chords, but there's a discrete number of them, countable infinite, say. And that you can also do in this way. You have to be a little bit more careful about what stable team isomorphism means, but things also work around in that case.
So no further questions, you can there is so much too.